So let's say we want to build a video calling feature in our app. We'll talk about how to implement this and the different ways to scale it up. The first case would be if we have the user A and user B, and they want to video call each other. The best protocol to use here would be peer-to-peer, and that means that the user A will talk to the user B directly without any intermediate servers. So the packets are going from the router on user A to the router on user B, and the routers are sending the data over to the user B and sending it to the user A. And that means that we don't have any intermediate layers between the two users, and the video feed is being directly sent over from each user to the other user. And this is the best case scenario, as we don't have any latency related to processing or having to stream that video feed over from an intermediate server here. So this is the best case scenario using peer-to-peer. And how does peer-to-peer work exactly? So let's discuss the different techniques that we can use to implement this. Peer-to-peer connections can be done using two of the most common protocols. The first one is UPnP, and the second one is UDP hole punching. So the best protocol for this audio calling or video calling feature would be using UDP and not TCP. There is a technique named TCP hole punching, but we won't discuss that now, as UDP is the better protocol for audio calling or video calling. And the reason for that is when you have a video call with someone, if you lose some of the data related to network fluctuations or packet losses or anything like that, you don't really care and you don't really need to retrieve that piece of data again. You can just display a lower video quality to the user, or there's some dropped packets. It's fine because it's a real-time call and we don't really care about the data that's being lost. So UDP would be the best for that. What does UPnP mean and what does UDP hole punching mean? So UPnP is a protocol that is supported by most routers in the homes of people, and it allows us to communicate with the router and tell the router that whenever you receive a packet on a certain port, this packet is actually meant for me, so send it over to me and don't just drop it. So let's say you're user A, and you are usually behind a router. This router has a firewall. User B has the same thing, is behind a router, and the router still has a firewall. So what we can do is user A communicates with the router using the UPnP protocol, and user B communicates with the router using UPnP. And we tell the router that we want the port, for example, 9000, to be open, and we want this port to direct all the data that's coming to it to me. And the same thing goes for user A. So this is the easiest way, and UPnP is just a simple API. It's based on XML. It's nothing too crazy, nothing like, you don't really have to implement a lower level implementation of this. You can just use the API that the router gives you, and you can communicate with the router doing that. And what we can do is, once we have the ports open, we can exchange our IPs, our public IPs, using an intermediate server. Let's say we have the server here, and the server knows the public IP of B and the public IP of A. So it just relays that data over to each one, and we know that the port is open now, so we just have a direct connection between the two users, and we don't really need to communicate with the server anymore. And this is the easiest way to do this, but usually UPnP is sometimes blocked. It's not supported on all routers, and some ISPs don't allow you to use UPnP or use specific ports on your router for security reasons or just for ensuring some policies in the network. So it's not always feasible to use ePMP, and that's why we have UDP hole punching and TCP hole punching. So what is UDP hole punching? To understand it, we have to talk about NATs. So what is the NAT? The NAT is an acronym for Network Address Translation. And this is basically a table that the router keeps inside of itself to let it know which ports need to redirect to which devices. And this happens because if I'm A, for example, and I want to connect to an outside server, I have to go through my router first. This is the router. I make that call first to the router, and the router makes it to the internet. So usually when we make a call like that, we expect a response, but that response won't go to A directly. It would first have to go through the router. So whenever we receive this response, the router has to forward it back to A. How can we achieve that? So whenever we send a request on port, let's say 8000, we have a specific port open in a router for a short period of time that tells the server here that you can reply on this specific port. And for example, let's say it's 9001. So along with the request, we have a port that the server can reply to. And the router can keep this port inside a table. Let's say our RP is 192.168.1.107. So the router in its NAT table keeps an entry that says the IP 192.168.1.107 expects to receive a response on a port 9001, and we need to forward this response on the port 8000, for example. So we send our request, it's saved in a NAT, and whenever the server returns a response, we get this response, and then we look it up in the NAT, and we see that, yeah, the port 9001, we expect this data to come, and we can send it over to this IP address, which is user A. So effectively, what we have done is we punched a hole through the router's firewall, and we told it that when you get a response or when you get a packet on this IP, you should send it to this internal IP of A. So this is what hole punching is really about. And we can achieve that by having an intermediate server. So let's say this is user A, this is user B, and both go to a server named the turn server. So the turn server knows the public IP address of both B and A. And it also knows that the ports that they punched a hole through the NAT with. So we take this data and we relay it to each different users. So for B, we send it the data related to A, which is the IP address, the public IP, and the port that we have punched a hole through. And we do the same for A. We send it the data of B, which is the IP, and the port that we have just punched a hole through. And then A and B can use that data to establish a direct peer-to-peer connection with each other. And this is basically how UDP hole punching works, and this is a very common technique to achieve peer-to-peer connections. So let's talk about how we can scale that. In the case of A and B, it's a really small scale because you just have a direct connection between A and B, and it's best case scenario because you don't have any latency of having to process anything on a central server. You can just relay the data from A to B and from B to A directly. But when you start to scale this up, let's say you have Discord, for example. You're on a voice channel, and this voice channel has 4 users. So this is user 1, user 2, user 3, and user 4. And how Discord works, whenever a user speaks, you have to send the data to the other users. So let's say user 1 is speaking, and now we have to forward this data to user 2, 3, and 4. And if this is just peer-to-peer, you have to send the same piece of data 3 times over. And this means that you have to send more throughput, and this might introduce latency in the network if we have more and more users joining in. So pure peer-to-peer is not very scalable. So how can we scale this up? There are 3 techniques that we can scale it up with. So we can use peer-to-peer mesh network. This is the first technique, and basically what it means is user 1 doesn't have to send the data to all the users, it just has to send it to a predefined number of users. Let's say we have to send it to 2 users only, and each user sends it to another 2 users, which is like 4, 5, and this sends to user 6 and user 7. It looks like a tree, but it's a mesh. So in that case, we don't really have to send the data over to 6 users. We just send it to 2 users and they send it to the other 4 users. And this is a mesh network. It's fine, you can get away with it, but it doesn't scale very well as well, just as peer-to-peer. The other 2 techniques are for high scaling applications. And the first one would be using an SFU, and this is an acronym for Selective Forwarding Unit. And basically what this does is it takes the data from user 1, for example, it goes to SFU, and then the selective forwarding unit is responsible for sending the data over to all the users that are connected in the call. So this is user 2, 3, 4, 5, 6, whatever. And you can do that to scale your service up. And it's great to do that. But when you start to have problems with this is whenever you have multiple users speaking at the same time or showing a camera or opening a video feed or sharing a screen, you can start to run into some problems with the selective forwarding unit. Because in the case of Discord, only one user is speaking at one time, maybe 2 users, maybe 3. It's not a large number unless you're in a big channel. But usually it's a small number of users speaking at the same time, if not only one. So it's kind of fine to use an SFU. But when you start to have large conferences, for example, having a meeting, you kind of have to use an MCU. An MCU is responsible for processing the media and combining it together and then sending it to the users. So imagine this scenario. We have user 1, user 2, user 3, user 4, user 5. And all the 5 users have their camera open. And we have about 50 other users in the call. So if we use an SFU in that case, we have to send 5 video feeds to 50 users. And if we do the math, that's 500 video streams streamed from the SFU. And this can get pretty nasty pretty quickly. So the alternative would be to use an MCU. And what an MCU would do is it would take the video feed from the 5 users and combine it into one video feed. And then it will send this over to the 50 users. So instead of sending 500 feeds, we now send 50 only. So this is what an MCU does, and it significantly improves our scalability. And the scalability of an MCU or an FCU depends on your backend architecture and how you're working with it. And these are the different ways to scale up an audio call or a video call. So going back to peer-to-peer, there's something that I forgot to mention. And let's revise what kind of different technologies that we can use here. So first, with peer-to-peer, we have to use a stun server, and this is the server responsible for exchanging the session data between two users to making them able to connect to each other. Whether you're using UPnP or UDP hole punching, you have to use a stun server. And WebRTC is one example of a library that does this on its own. It does this automatically for you, so you don't really have to worry about this. And WebRTC is great, but you have to use a stun server either way. And you also can use a relay server. And a relay server is just like a backup. If you can't establish a peer-to-peer connection, you can use a relay server as a backup. And what it does is basically user A, if it can't connect directly to user B, it sends it to the relay server. And the relay server is responsible for sending that data over to B, and B can send this data to the relay, and the relay can send it back to A. So it looks like an SFU, but on a much smaller scale. So these are the techniques that we can use for peer-to-peer. We also have UDP hole punching, and we have UPnP. In the case of scaling the calls up, we can use an SFU or an MCU. So these are the topics that we discussed. Thank you.